We're going to do a practice of trig substitution here. So we're going to find the integral of 1 over the square root of 4x squared plus 9 dx using trig substitution. And what you'll see is that I have the rules for trig substitution over here on the side just to help us draw our triangles. So one big clue into I'm going to need trig substitution is that we have a square root of some sort of a squared plus u squared or u squared plus a squared. Anyways, we have some sort of square root that looks like it could be a hypotenuse or a leg of a triangle. So that's what clues us into the u substitution. Now, looking at a right triangle, we know that if this is a right triangle, a squared plus b squared gives us c squared. And that being said, if I know what a is and I know what b is, I could figure out what c is. C is going to equal the square root of a squared plus b squared. And so that helps me figure out where things go on the triangle. So here, I have this right here, the square root of 4x squared plus 9. And that looks like it's definitely going to be a hypotenuse of a triangle. So if I were to draw out a triangle here, the hypotenuse is going to be the square root of 4x squared plus 9, which means that one of the sides is going to be 3 and one of the sides is going to be 2x. How did I know that? Well, I took the square root of each component of that. Now, figuring out those sides is when we use these rules here. Which leg does it go on? Well, this rule says that our u is going to be the vertical leg and our a is going to be the horizontal leg. And really where these were derived were the ones that are going to give us sine, tangent, and secant. Because sine, tangent, and secant are going to give us positive integrals. Whereas if we would have had cosine, cotangent, or cosecant, then all of those would have given us negative integrals. So you certainly could set up this triangle in a different manner. You're just going to get one of those equivalent forms and it might be a little bit uglier. So our u is always the one that has a variable with it. So our u here is 2x. Now, how did I know it was 2x? Because u squared would give me 4x squared. That's how I knew it. And our a is going to be 3. And again, how did I know that? Because a squared would be 9. 3 squared would be 9. Okay, so now using right triangle trig, I could write all sorts of different ratios here. Well, tangent is opposite over adjacent. This is our opposite. This is our adjacent. And so the tangent of theta is going to be 2x over 3. That's kind of cool. Tangent of theta is 2x over 3. And using that, I could then figure out what theta is going to be. Not that I need to right now, but theta would be the inverse tangent of 2x over 3. And I could figure out what just x would be. I could figure out what just x would be because I could take this, and if I just wanted to know what is x going to be, well, I would multiply 3, and then I would divide by 2. So all of these things come from drawing this triangle. Now, how are those helpful? How are those helpful? Well, that's a really good question. Well, I could take what I know and I could replace things in here, and I could rewrite this whole thing in terms of theta instead of in terms of x. And maybe by rewriting it in terms of theta, it would make it easier to integrate. So let's look here. If this is what x is, I want to know what is dx so that I can replace that. So if I take the derivative of this, I would have 3 halves. Well, the derivative of tangent is secant squared of theta. And that's what dx equals. So I could go in and I could replace dx with 3 halves secant squared of theta. Okay? This rule also tells us that the square root of a squared plus u squared is a secant of theta. Well, that's helpful because I could replace this whole thing with a times secant of theta. Okay, so let's rewrite our integral. And let me try to use some colors here so you can see exactly what I'm doing. This is going to replace this. So let's go ahead and just do that. The integral of, let's pull the 3/2 out front, secant squared of theta d theta. And then let's pick a different color highlighter here. This is going to be replaced with this. And so we're going to divide that by, well, a is 3, and then we're going to have secant of theta. Okay, so the 3 will cancel out of the top and the bottom, and one of the secants will. And so I'm going to have 1/2 the integral of secant of theta d theta. Okay, that's not so bad. Now I just need to figure out what is the integral of secant of theta d theta. And let's see if we can pull up our basic integration rules, because I'm pretty sure that that is a part of our basic integration rules. Tell me if you see it. There it is. Okay, and so on here we are looking for the integral of secant of theta, and there it is. It's number 12. Number 12. So we have 1/2 times ln of secant of theta plus tangent of theta plus c. Okay, now we only have one more step. We want our final answer to be in terms of x, because we started in terms of x. We don't want to change its identity, right? So we want to figure out what is secant of theta. Well, secant of theta is the hypotenuse over the adjacent. So I can replace secant of theta, with this. And then we know what tangent of theta is. We know what tangent of theta is because we had that written down earlier. And so I can replace tangent of theta with that. So my final answer for this becomes 1/2 ln of the square root of 4x plus 9 over 3 plus 2x over 3 plus c. And we are done. That is our final answer.